Determining the appropriate ampere interrupting capacity, or AIC, rating for a circuit breaker is a crucial aspect of electrical system design, especially when dealing with high-power applications such as supplying power to lighting pedestals in a marine environment. The AIC rating signifies the maximum fault current that a circuit breaker can safely interrupt without being damaged or causing a hazardous situation. When selecting a circuit breaker, it is imperative to ensure that its AIC rating exceeds the calculated or known available fault current at its point of installation. Insufficient AIC ratings can lead to catastrophic failures during a fault event, resulting in equipment damage, fire hazards, and potential injury to personnel. In this context, we are examining a 150 kVA, 480 volt to 280-120 volt 3-phase, 60 Hz circuit breaker intended to feed new lighting pedestals in a marina. The required AIC rating for this particular application is 125 AIC. To fully understand the implications of this rating, let's delve into the steps involved in calculating fault current and the factors influencing AIC rating selection. Firstly, calculate the full load current of the transformer. The formula for calculating the full load current in a three-phase system is KVA multiplied by 1000 divided by the square root of 3 multiplied by the voltage. In this instance, it's 150 kVA multiplied by 1000 divided by the square root of 3 multiplied by 480 volts, which equals approximately 180.4 amps. Secondly, determine the transformer impedance. Transformer impedance, typically expressed as a percentage, represents the transformer's opposition to current flow during a short circuit. This value is crucial for calculating the available fault current at the secondary terminals of the transformer. The impedance value is usually found on the transformer's nameplate. For this example, let's assume a standard impedance of 5% or 0.5 per unit. Thirdly, calculate the fault current at the secondary. The formula to calculate the symmetrical fault current at the secondary is the full load current divided by the transformer impedance. In our case, that's 180.4 amps divided by 0.5, which equals 3608 amps. This represents the theoretical maximum symmetrical fault current available at the transformer secondary terminals. Fourthly, consider the available fault current from the utility. It is essential to obtain the available fault current from the utility company at the point of service. This information is critical because the utility's contribution to the fault current can significantly impact the overall fault current level at the equipment. The utility will typically provide this value in amps. This value should be obtained from the power utility company and its documentation. Fifthly, determine the worst-case bolted fault current. To determine the appropriate AIC rating, one must identify the worst-case bolted fault current. This is the highest possible fault current that can occur at the equipment. This takes into consideration factors such as transformer impedance, utility source impedance, and conductor impedance. Sixthly, apply appropriate safety factors. Industry best practices and electrical codes often mandate the application of safety factors when selecting AIC ratings. These safety factors provide an additional margin of safety to account for uncertainties in fault current calculations and potential future increases in system loading. Electrical codes such as the National Electrical Code, or NEC, provide guidelines for selecting appropriate AIC ratings. Seventhly, select the appropriate circuit breaker AIC rating. Once the maximum available fault current is determined, select a circuit breaker with an AIC rating that meets or exceeds this value. The provided AIC rating of 125 AIC seems extremely low. Based on the calculation above of 3608 amps, that would not be sufficient. It is important to select a circuit breaker with an AIC rating sufficiently high to handle the maximum potential fault current. Several factors influence the selection of an appropriate AIC rating. These factors include the transformer size, impedance, the utility's available fault current, conductor size and length, and any other impedance in the fault current path. The location of the circuit breaker within the electrical system also plays a role, as fault current levels typically decrease with distance from the source due to impedance in the conductors. In a marine environment, additional considerations come into play. Marinas are often exposed to harsh environmental conditions, including saltwater, humidity, and temperature variations. These conditions can accelerate corrosion and degradation of electrical equipment, potentially increasing the risk of faults. Therefore, it is essential to select circuit breakers that are specifically designed and rated for use in marine environments. These circuit breakers typically feature corrosion-resistant materials and construction to withstand the challenges of the marine environment. The National Electrical Code, specifically Article 555, addresses the specific requirements for electrical wiring and equipment in marinas and boatyards. This article provides guidance on selecting appropriate AIC ratings, grounding and bonding requirements, and other safety measures to ensure the safe operation of electrical systems in these environments. In addition to selecting circuit breakers with appropriate AIC ratings, regular inspection and maintenance are crucial for ensuring the continued reliability and safety of electrical systems in marinas. This includes visually inspecting circuit breakers for signs of damage or corrosion, testing their operation to verify proper functionality, and tightening connections to prevent loose connections that can lead to overheating and faults. Furthermore, it is important to ensure that all electrical work in the marina is performed by qualified and licensed electricians who are familiar with the specific requirements of marine electrical systems. These professionals can properly assess the available fault current, select appropriate circuit breakers, and install and maintain the electrical system in accordance with applicable codes and standards. To summarize, the AIC rating is a critical parameter for circuit breaker selection, ensuring that the breaker can safely interrupt fault currents without causing damage or hazards. For a 150 kVA 480 volt to 280-120 volt three-phase circuit breaker supplying lighting pedestals in a marina, a careful assessment of the available fault current is essential. A value of 125 AIC seems extremely low for this application. A thorough calculation considering all relevant factors, including transformer impedance, utility contribution, conductor impedance, and marine environmental conditions, must be performed to determine the appropriate AIC rating. Consulting with a qualified electrical engineer or electrician is highly recommended to ensure the safe and reliable operation of the electrical system.